Hello, PreCalc. Here we are with 3.5, day 1. It's a whole day of story problems. In fact, it's going to be 2 whole days of story problems and maybe even 3. Okay? It's exponential and logarithmic models. Everybody always complains, when are we going to use this? Here it is. Here it is. Okay? Now, granted, these are going to be dumbed down a little bit so that they nicely cooperate with what we're studying. But here's real-world problems and how you would model these real-world situations with the functions that we've been recently studying. Okay? The 5 most common types of mathematical models involving exponential functions and logarithmic functions are as follows. Exponential growth and exponential decay. We've talked about those before. Okay, exponential growth, we're going up and up and up. Exponential decay, we're coming down, 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 down. Okay. Gaussian model kind of goes up and back down. Okay, then we have the logistic growth model. And this kind of disappeared on us, didn't it? Didn't print off. I will do my best to write this, but you know my handwriting is that of a probably 2nd or 3rd grader. A on top, 1 plus B times E to the negative Rx, rate times x, negative Rx. And there is our logarithmic models using natural log or log. Okay? So our logistics growth model kind of has a horizontal down here at 0, and then it will have a horizontal asymptote also at your A value. Exponential growth has a horizontal at 0 on the left and goes up to the right. Exponential decay has a horizontal asymptote at 0 as you go to the right and goes up forever to the left. Gaussian model kind of looks like that little roller coaster hill in the middle. Or a little normal curve if you've done stats. Natural log is a little bit smoother. It looks like of a curve up and to the right, and log is going to be pretty sharp, almost a 90-degree turn in there. But they both have vertical asymptotes and not horizontal asymptotes. Okay? You can gain quite a bit of insight into the situation modeled by an exponential or logarithmic function by identifying and interpreting the function's asymptotes. Use the graphs above to help identify the asymptotes of the graph of each function, and then you can kind of match what kind of asymptotes you're using or what kind of asymptotes are present in your data, and then match it to the graph up here as the base kind of model of the function you're going to use. All right. Example 1. Estimates of the amounts in billions of dollars of U.S. online advertising spending from 2007 to 2011. A scatter plot of the data is shown. Okay. An exponential growth model that approximates these data is given by this. So here is your exponential growth model. So if it's exponential growth, we're kind of flat, but we are starting to take off. Okay, so we're kind of over in here. We're just about ready to go crazy. And think about, 2007. How old were you guys in 2007? That's crazy. 2007, I was graduating from college. And I can tell you there was not a whole lot of advertising Facebook had 0 ads at that time. Crazy. Yep, and now it's 2022, and let's see, there's an ad banner at the very top of ESPN. There is targeted ads for whatever topic of conversation your phone has heard you or listened in on you talking about with your friends. You'll have targeted ads for that as soon as you open up Facebook and Twitter. It's crazy. It's crazy now. So yeah, it would totally make sense that like 2007 to 2011 were flat, and it's about to go nuts. 2022, whoosh, way up there probably. Okay? According to this model, when will the amount of U.S. online advertising spending reach $40 billion? Okay, so spending is going to be our S. It's going to be 40. So 40 equals 10.33 E. Nope, not there. Big E on the ground. And then this tiny little decimal power times T is in the air. 0.1022 T. Okay? Let's solve. Well, we want to get rid of the E. And I know I'm already jumping all over this. E, natural log. But before we do that, we got to move this. So let's divide by the 10.3. E to the 0.1022 T. Alrighty, natural log both sides. I'm going to put parentheses around it so I don't forget to so I don't accidentally do natural log of 40 and then divide by that. Okay, if you want to be real mathy about it, this stuff comes down first with the power property. Natural log of E is going to be 1 because natural log is log base E, so log base E of E is 1, and then we're just left with that. If you don't care about the mathy part and you're trying to do the shortest possible way, you can just think about it as natural log and E cancel out, and that falls down. Alright, and then we're going to divide by the 0.1022. And now we're going to carefully type this in. Alright. So natural log of... Now someone else showed me an even shorter way. What was it? Is it alpha this one? It is. Instead of going alpha y equals first option, if you just do alpha and then the variable button, it just jumps right to your fraction bar. That's crazy. Okay, 40 over 10.33, bump it out, close it. If you wanted to, you could tack on the divided by 0.1022 now. I kind of want to just see this, and then divide by 13.25. We'll round it to 13.25 because that fits nicely. Years, because 13 years and 0.25 would be 4 months, right? So we'd be looking at 2013, and let's see, 0.25, a fourth of a year, 3 months, so like the end of March or beginning of April, I guess. So if you want to get real specific. Alright, let's do another one. These are fun. Story problems are fun. All right. In a research experiment, we got some fruit flies. I can't stand fruit flies. Increasing according to the law of exponential growth. After 2 days, there are 125 flies. And after 4 days, there are 350 flies. How many will there be in 6 days? So you got to use the given information and come up with the equation, and then from the equation go forward and figure out 6 days. Okay? So let's do it. We have 2 giving us 125. And 4 gives us 350. And our base equation for exponential growth, a times e to the bx. Okay, and we just know our x and y. So we have 125 equals a times e, and we're going to turn it around. It does say bx, but we know x, so we're going to put 2b. And we also have 350 equals a times e to the 4b. Okay. Well, we're going to take you back to Algebra 2. We're going to do a little substitution to help us solve. Okay, so we're going to get we're going to substitute in for a, and use that to solve for b. And we'll probably end up with some decimal approximations or some crazy numbers in there along the way, but we'll make it work. Okay, so if we're going to solve for a in the first one, we would just divide by e to the 2b. Right, divide by that. So a is going to be 125 over e to the 2b. Okay, so let's substitute this in for a in the other one. 350 equals 125 over e to the 2b times e to the 4b. Well, we have e to the 4b on top, e to the 2b on the bottom. Let's think about if we just had like 2 to the 4th on top and 2 to the 2nd on the bottom. 2, 4, 8, 16 over 4 is 4, which is 2 to the 2nd. Okay? Or if you're thinking about your exponent properties, alright, we can subtract. With division, you get to subtract your exponents if they are common base, which these are. They're both e, so 4b minus 2b is going to be e to the 2b. We're going to divide by 125, and we get 2.8. We'll natural log. So now we'll have natural log of 2.8 equals 2b, divide by 2, natural log of 2.8 over 2 equals b. Okay? So there's our b. Now, a equals 125 over e to the 2b. 2 times natural log of 2.8 over 2. So the 2 times over 2 is going to cancel out. We're running out of room quick, aren't we? Sorry. A equals 125 over e to the natural log of 2.8. Now we're going to go with the decimal on this. We could probably go with the decimal on b as well. A is 125 divided by e to the natural log of 2.8. 44.64. Should we do a decimal for b? Natural log of 2.8 divided by 2. 0.515. What was the other one? 44.64. Let's go 3 decimals. 3. And now we can fill in our equation. And remember, we're trying to get 6 days. So we have y equals a 44.643 times e to the power of b 0.515 times x, and x is 6 days. Not bad, 981. Answer key had 980, they didn't round. We rounded, we had an extra fruit fly. It's okay. 981. Alright. We're approaching 20 minutes. That's usually where I like to keep it. The way these are going, it goes a little, well, you know what? This one looks pretty short. Let's try it. We're at 1740. We can do it. We can keep it at 20 minutes. That'll be a nice cut spot. Estimate the age of a newly discovered fossil in which the ratio of carbon 14 to carbon 12 is R equals 1 over 10 to the 14th. And where R equals 1 over 10 to the 12th times E to the negative T over 8,223. Okay? So, this is where we want to be. This is our ratio, and this is the formula given your time t. Alright? So we have 1 over 10 to the 14th. And over here, it's 1 over 10 to the 12th times E to the negative T over 8,223. Okay? Well, we see E, we know the variable's in E, we know what we need to do. We're going to natural log that to get the variable down. But we have this multiplier in the front. Okay, 1 over 10 to the 12th. Let's multiply both sides by 10 to the 12th. And that will cancel out the 1 over 10 to the 12th. 10 to the 12th divided by 10 to the 14th. 14 minus 12 is going to be 2. So we have 1 over 10 squared. Okay? 10 to the 12th on top, 10 to the 14th on the bottom. When you're dividing, you can subtract exponents. I like to do big minus small. 14 minus 12 is 2. Put the answer where the bigger one was. It was on the bottom. You could just do straight up 12 minus 14 and have 10 to the negative second, which is the same thing as 1 over 10 squared. Does not matter. It's the same thing. Up to you. Okay? E to the negative t over 8223. Now we're going to natural log. So we have natural log of 1 over 10 squared equals negative t over 8,223. Well, I want regular t. So I'm going to multiply by this with a negative. So that should take care of my negative and my number. Uh, 1 over 10 squared, 1 over 100, or 0.01. Negative 8,223 times natural log of 0.01. 37,868 years. That's an old fossil. Well, maybe not that old as far as fossils are concerned. 37,868 years. And there's a good stopping point. 22 minutes. I went over. Sorry, kids. I'm sure you will be fine. Okay? Do your best. Try to get a couple of these story problems done on your own. And we'll see you next week.